ground fault circuit interrupter, or GFCI, is a safety device that monitors the electrical current flowing through a circuit. It trips if it detects a difference between the current flowing in the hot and neutral wires. When ground fault circuit interrupters are connected in a multi-circuit setup, they can interact with each other if they share a neutral wire. If a fault occurs on one circuit, the ground fault circuit interrupter on that circuit will trip. However, if the neutral wire is shared with another circuit, the fault current can flow through the neutral to the other circuit, causing the ground fault circuit interrupter on that circuit to trip as well. This is why a ground fault circuit interrupter cannot share a neutral on a multi-circuit. To prevent this issue, each ground fault circuit interrupter should be installed on its own circuit with its own dedicated neutral wire. This ensures that if a fault occurs on one circuit, only the ground fault circuit interrupter on that circuit will trip. It is important to ensure that the neutral wires used for ground fault circuit interrupter circuits are properly sized and connected. Using undersized or poorly connected neutral wires can also lead to ground fault circuit interrupter tripping issues. If there are ground fault circuit interrupter tripping issues, it is recommended to have a qualified electrician inspect the wiring and connections to ensure they are correct and safe. Let's delve deeper into the reasons behind this prohibition and the implications of improper wiring. Understanding the function of a ground fault circuit interrupter. A ground fault circuit interrupter is designed to protect people from electrical shock. It does this by monitoring the balance of current between the hot, or energized, conductor and the neutral conductor. In a properly functioning circuit, the current flowing out on the hot wire should equal the current returning on the neutral wire. If there is a difference, even a very small one, it indicates that current is leaking somewhere other than through the intended load. This leakage is called a ground fault and often occurs when current flows through a person's body to ground. Ground fault circuit interrupters are incredibly sensitive and are designed to trip, interrupting the circuit when they detect a current imbalance of as little as 5 milliamps. This rapid interruption can prevent serious injury or even death. The problem with sharing a neutral and multi-wire branch circuits. A multi-wire branch circuit, or NWBC, consists of two or more ungrounded conductors that share a common neutral conductor. These circuits are typically used to provide 120 volts power from a 240 volt source, such as in a residential electrical panel. The advantage of using an MWBC is that it allows for more circuits to be run with fewer wires, saving on materials and labor. However, when ground fault circuit interrupters are involved, sharing a neutral on an MWBC creates a problem. The ground fault circuit interrupter monitors the current balance on the entire circuit it protects. When two circuits share a neutral, the ground fault circuit interrupter cannot distinguish which circuit the imbalance is occurring on. As mentioned earlier, even a small current leakage on one circuit can cause the ground fault circuit interrupter on both circuits to trip. This is because the neutral is carrying current from both circuits. The ground fault circuit interrupter perceives this combined current as an imbalance, even if the other circuit is functioning correctly. This leads to nuisance tripping, which is not only inconvenient but can also be dangerous if it interrupts power to critical equipment. The solution: dedicated neutrals for ground fault circuit interrupters. The solution to this problem is to ensure that each ground fault circuit interrupter has its own dedicated neutral conductor. This means that the neutral wire for each circuit protected by a ground fault circuit interrupter must run independently back to the neutral bus bar in the electrical panel. While isolating the neutral conductors, the ground fault circuit interrupter can accurately monitor the current balance on its own circuit without being influenced by other circuits. When a ground fault occurs on one circuit, only the ground fault circuit interrupter protecting that circuit will trip, leaving the other circuits unaffected. This eliminates nuisance tripping and ensures that the ground fault circuit interrupter functions as intended, providing reliable protection against electrical shock. Additional considerations: proper wiring and connections. Even with dedicated neutrals, it is essential to ensure that the wiring and connections for ground fault circuit interrupter circuits are properly installed. Loose or corroded connections can create resistance in the circuit, leading to voltage drops and current imbalances. These imbalances can cause the ground fault circuit interrupter to trip unnecessarily. All connections should be tight, clean, and free from corrosion. It is also important to use the correct size wire for the circuit. Undersized wires can overheat and cause voltage drops, which can also lead to ground fault circuit interrupter tripping issues. The wire size should be determined based on the circuit's ampacity and the applicable electrical codes. Ground fault circuit interrupter compatibility. Not all ground fault circuit interrupters are created equal. Some ground fault circuit interrupters are more sensitive than others and may be more prone to nuisance tripping. It is important to choose ground fault circuit interrupters that are appropriate for the application. For example, ground fault circuit interrupters used in areas with high levels of electrical noise, such as industrial environments, should be less sensitive than those used in residential settings. Additionally, some ground fault circuit interrupters are designed to be used with specific types of loads. For example, some ground fault circuit interrupters are designed for use with electronic equipment and are less likely to trip due to transient voltage spikes. Testing ground fault circuit interrupters. Ground fault circuit interrupters should be tested regularly to ensure that they are functioning correctly. Most ground fault circuit interrupters have a test button that can be used to simulate a ground fault. When the test button is pressed, the ground fault circuit interrupter should trip, interrupting the circuit. If the ground fault circuit interrupter does not trip when the test button is pressed, it should be replaced immediately. Ground fault circuit interrupters should be tested at least once a month, and more frequently in areas with high levels of electrical activity. Troubleshooting ground fault circuit interrupter tripping issues. If a ground fault circuit interrupter is tripping frequently, it is important to troubleshoot the problem to determine the cause. The first step is to identify which circuit is causing the ground fault circuit interrupter to trip. This can be done by turning off all of the breakers on the circuit protected by the ground fault circuit interrupter and then turning them on one at a time until the ground fault circuit interrupter trips. Once the circuit causing the problem has been identified, the next step is to inspect the wiring and connections on the circuit. Look for loose or corroded connections, damaged wires, and any other signs of electrical problems. If any problems are found, they should be repaired immediately. If the wiring and connections appear to be in good condition, the problem may be with the load connected to the circuit. Try disconnecting all of the loads from the circuit and then reconnecting them one at a time until the ground fault circuit interrupter trips. This will help to identify which load is causing the problem. If a particular load is causing the ground fault circuit interrupter to trip, it may be defective and need to be replaced. When dealing with electrical circuits and devices, it's crucial to prioritize safety. Here's an expanded discussion on electrical safety, including safe work practices, personal protective equipment, and lockout/tagout procedures. Safe work practices. Electrical work can be hazardous if not performed correctly. Always follow safe work practices to minimize the risk of electrical shock, arc flash, and other electrical hazards. Firstly, de-energize circuits before working on them. Whenever possible, de-energize the circuit you will be working on. This involves turning off the breaker or removing the fuse that supplies power to the circuit. Use a voltage tester to verify that the circuit is de-energized before you begin working on it. Secondly, use insulated tools. When working on or near energized circuits, use tools that are specifically designed for electrical work. These tools have insulated handles that protect you from electrical shock. Thirdly, avoid working in wet conditions. Water is an excellent conductor of electricity. Avoid working on electrical circuits in wet conditions, such as during rain or in damp environments. Fourthly, maintain a safe distance from energized parts. If you must work near energized parts, maintain a safe distance from them. The safe distance will depend on the voltage of the circuit. Consult the applicable electrical codes and regulations for guidance on safe distances. Fifthly, use proper grounding techniques. Grounding is an important safety measure that helps to protect against electrical shock. Ensure that all electrical equipment is properly grounded. Personal protective equipment or PPE. Personal protective equipment is essential for protecting workers from electrical hazards. The type of personal protective equipment required will depend on the specific task being performed and the potential hazards involved. Firstly, safety glasses or face shields. Wear safety glasses or a face shield to protect your eyes from arc flash and other electrical hazards. Secondly, insulated gloves. Wear insulated gloves to protect your hands from electrical shock. The gloves should be rated for the voltage of the circuit you will be working on. Thirdly, insulated clothing. Wear insulated clothing, such as a long-sleeved shirt and pants, to protect your body from electrical shock. Fourthly, insulated footwear. Wear insulated footwear to protect your feet from electrical shock. Fifthly, hearing protection. Wear hearing protection, such as earplugs or earmuffs, to protect your ears from loud noises, such as those produced by arc flashes. Lockout/tagout procedures. Lockout/tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. These procedures involve isolating the equipment from its energy source and then locking and tagging the energy isolation device to prevent it from being turned on. Firstly, identify the energy sources. Identify all of the energy sources that supply power to the equipment. This may include electrical, mechanical, hydraulic, pneumatic, and other energy sources. Secondly, isolate the energy sources. Isolate the equipment from all of its energy sources. This may involve turning off breakers, closing valves, or disconnecting other energy isolation devices. Thirdly, lock out the energy isolation devices. Place a lock on each energy isolation device to prevent it from being turned on. The lock should be unique to the individual performing the maintenance or repair. Fourthly, tag out the energy isolation devices. Place a tag on each energy isolation device that indicates that the equipment is being worked on and that the energy isolation device should not be turned on. Fifthly, verify the isolation. Verify that the equipment is properly isolated from all of its energy sources before beginning work. This may involve using a voltage tester to check for voltage on electrical circuits or testing the pressure in hydraulic or pneumatic systems. By following these electrical safety guidelines, you can minimize the risk of electrical hazards and ensure a safe working environment. It is always recommended to consult with a qualified electrician for any electrical work, especially when dealing with ground fault circuit interrupters and multi-wire branch circuits. They can ensure that the wiring is correct, safe, and compliant with local electrical codes. The importance of adhering to electrical codes and standards cannot be overstated. These codes and standards are designed to ensure the safety of people and property by providing guidelines for the installation, maintenance, and operation of electrical systems. They cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Firstly, the National Electrical Code, or NERC. The National Electrical Code is the most widely adopted electrical code in the United States. It is a comprehensive set of rules and regulations that govern the safe installation of electrical wiring and equipment. The National Electrical Code is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. Secondly, Underwriters Laboratories, or UL. Underwriters Laboratories is an independent organization that tests and certifies electrical product. Underwriters Laboratories listed products have been tested to meet Underwriters Laboratories safety standards and are considered to be safe for their intended use. Thirdly, the Institute of Electrical and Electronics Engineers, or IEE. The Institute of Electrical and Electronics Engineers is a professional organization that develops standards for a wide range of electrical and electronic technologies. The Institute of Electrical and Electronics Engineers standards are used by manufacturers, engineers, and other professionals to ensure the safety and reliability of electrical and electronic systems. Fourthly, the National Fire Protection Association, or NFPA. The National Fire Protection Association is a non-profit organization that develops codes and standards for fire prevention and safety. The National Fire Protection Association codes and standards are used by fire departments, building officials, and other professionals to ensure the safety of buildings and other structures. Adhering to electrical codes and standards is essential for ensuring the safety of electrical systems. These codes and standards provide a framework for the safe installation, maintenance, and operation of electrical equipment. By following these guidelines, you can minimize the risk of electrical shock, fire, and other electrical hazards. In conclusion, ground fault circuit interrupters are essential safety devices that protect people from electrical shock. However, they must be installed correctly to function properly. Sharing a neutral on a multi-wire branch circuit can cause ground fault circuit interrupters to trip unnecessarily. To prevent this, each ground fault circuit interrupter should have its own dedicated neutral conductor. It is also important to ensure that the wiring and connections for ground fault circuit interrupter circuits are properly installed and that the ground fault circuit interrupters are tested regularly. When in doubt, consult with a qualified electrician to ensure that your electrical system is safe and compliant with local codes.